There is not enough battery in this mic. Okay, I hope it will be okay. But if there is a problem in recording,
I'm sorry, we can't hear you. The sound is gone.
do you hear me in this one? Is this better?
Yes, yes.
Okay, and there is some chance that again it will turn off because there is not enough batteries in these mics. So if it's like this, just open your mic or write a WhatsApp question. Okay, so I don't want to speak too much about logistics, and the reason for that is that we were talking so much about that. I just sent you, and please just read the instructions. Just about participation. I don't care if you don't come to my classes. I don't care if you just want to watch videos and come to reinforcement. Really, I don't care. But you should just know, as someone who performed their first degree by studying almost alone and virtually, it's really, really, really hard. And the best thing about coming here is that we have these great discussions and we can talk about science. And this is something that I cannot do just by writing or explaining or everything. So you have the representatives, Sophie and Noah. Any problem, please talk to them. By the way, most of the course is not here, right? Okay, no problem. It's okay. As I said, I don't care. So we have 4 subjects that I want to talk about today. One of them is a subject that there is a chance that I'm going to proceed is hard regarding the question of SNR and how we measure it. And I just want you to say that as far as I see it, if I won't make it during the recitation, talking about all the subjects in the recitation note, I want you to read it yourself, okay? Because I think it's at least, I don't know if we'll have time next time to talk about it. Just keep in mind that if we won't make something, you need to complete it by yourself. Okay, so this course is signal and data analysis and mainly signal analysis. And when we talk about signals, we need to know how these kind of signals are saved in the recording system that we use. So what you see here, that we have 2 ways to record a measurement from the brain. And the first one is by an array that we have here, an index of all the time points in which we saved our data. And here is the value, right? And then when we have this correspondent vector from the recording system, it looks like this. We have only the values over here. Okay, so this is one way to record data. And in this way, what we are doing might be one of the 2. Okay, Zoom people, I don't know how, please put your Zoom on a great screen or whatsoever, my video, because now I'm going to use the board. And if you still don't see, so tell me, I'll go out of the share screen. Yeah, I think that it's recorded.
We do see the
Yes.
whiteboard and the screen.
You don't see? Okay.
Should be fine. No. We do see.
Oh, you do see it?
Yeah, we saw this share screen and presentation or document.
And now you can just magnify my video, and I'll use this this board over here. So when we are sampling data, okay, for example, I want to sample the data of heartbeats of someone. How does heartbeats look like? They look like this. This is the ECG, right? And now when I record the data, I don't record the full signal by itself. I record dots from the signal. For example, I can record the dot here and another one here and here and here, right? And when I record, I don't take the full signal, but I take only parts of the signal, specific dots. And these dots, I take them by using something called delta function. Okay, now why are we interested in the delta function? We don't use it anymore in this course. The reason we talk about delta function is just that it's another terminology for talking about sampling and sampling rate. So the delta function is how the recording devices are working. Because practically, they are not just, okay, I'm sitting here in the space, and when I see that the time is 1, I'll tap and save something. What happens practically is that these kind of devices have an electronic, electrical engineered parts in which they use the delta chronometer to save time points based on what the user wrote the system that she needs to save, okay? So the thing with this delta function, although it's a lot of math, the thing is just to remember that your recording devices, they do not collect all of the data. They sample it by defined dots, okay? Now, what is the problem with that? This means that we don't really collect data. All these graphs are practically interpolation, right? So I have the dot here and the dot here and the dot here, all of which are measurements, are samplings, but my real data could look differently. For example, if I have these dots and I collect, let's have the blue, right? So we had something like this. For example, it's not that accurate as it looks here, but it doesn't really matter. So one interpolation would be this blue line, and another possible interpolation will be this more curved line, and another interpolation could look like this, right? And another possibility might look like this. I'll take here the red. So we sample and we never know what is the real data. And the reason why we're talking about it is that this is a very, very elementary thing when we record the brain. Because our brain devices could use different kind of rates when we decide to record something. For example, calcium imaging signals are about, let's talk a bit about sampling rates. It's not in the notes as far as I remember. So sampling rate so this is given by hertz, right? What does this measurement says? So sampling rate, Fs, the frequency of sampling. This is 1 over, this is, the number of samples per 1 second. So hertz, these are the units for sampling rate. And this means the number of samples per 1 second. So for example, heartbeats are about 3 hertz per second. This means that within 1 minute, we have 3 cycles of heartbeats. A heartbeat, if this is 1 minute, will look like this. Okay? 2 to 3 times per second, we have these peaks and troughs over here of the heartbeats. Now, the question, if we know that this is 3 hertz, what is the duration between 2 peaks? Excuse me? 20 seconds between each peak? There are 3 peaks in 1 second, and each one of them is, it's okay. You were right if you were talking about 1 minute. But if it's 1 second, yes? Yes. Exactly. So you say that it's 1 second over 3 samples, right? So this is third second duration, right? And what size is it? A third second duration? It's around 300 milliseconds. Okay? So I want you to do it as fast as you can. When I wake up you in the middle of the night, and I ask you, what is the duration of a heartbeat if given the sampling rate, not the sampling rate, the frequency of 3 hertz, you have to say 300 hertz. And for example, when we talk about a gamma frequency, very important frequency in the brain that is used probably for attentional mechanism and so on. And this is 30 hertz. How many cycles of gamma frequency do we have in 1 second? We have 30 cycles, right? And what is the duration of each cycle? 1 over 30, which is about 30 milliseconds. Okay? So the relation is more clear now? Good. So what we want to understand is, how do I pick the sampling rate so I can really fully record the signal that I'm looking at? So for this reason, we need to understand how sampling devices look like. So some of them, their output will look like this. For example, in LFP or EEG or fMRI, you have a continuous signal that is sampled using the delta function, and you have this vector of numbers, and all of them are possible numbers. Okay, but another possibility is using devices that are sampling the spike trains. Okay, and you will see this kind of data already in your first project. And these devices, how they look like, it's 0 if there was no spike and 1 if there was a spike. Okay, so they record intracellular or extracellular, and you have this very strange vector in which, if there was a spike at this time point, it will be read as 1, and if there was no spike, it's 0. Okay, let's try to do it together. So we were already speaking about the delta. So, for example, I want us to try to do this one. Let's try to write the output of a recording device of spike trains of this kind of recording. So this is an intracellular recording in which we have for example, the membrane potential, also when there are no spikes, but also when there are spikes. Do you see? This is how a recording of the membrane potential looks like, right? And some of them are a subthreshold, which is under the threshold of spike, and some of them are suprathreshold, which are these spikes. So let's try to write the spike train of this neuron. So we'll have a table like this. And in this table, we have here the time. And this is spike. Was there a spike? So the first second is between 0 and 1, and another one between 1 and 2, another one between 2 and 3, 3 and 4, and 4 and 5. So instead of writing 0 to 1, 1 to 2, 2 to 3, and so on, we can just write the beginning of each duration, which is 0, 1, 2, 3, 4. How many spikes are there between 0 and 1? 1. So I write here 1. How many spikes are there between 1 and 2? No spikes, so I write 0. Between 2 and 3? Between 2 and 3? Here? 0. How many between 3 and 4? Okay, so it's this one. We have 1. And between 4 and 5? We write here only 1. Why? Although there is a possibility that our device will notice that there were 2 spikes, in our sampling grade, we did a binary equation. Spike or no spike? So I'm not interested in the number of spikes because my resolution is 1 second. So I only care if there was a spike or not. And this is how we write spike trains, okay? So how would you recommend me to record 2 spikes so that I can have a better resolution, that I can see the differences between the 2 spikes? What should I do? Smaller pieces. So you're offering me to take, so here it was 1 sample per second. So here it's 1 hertz. So you're offering me take more samples within each second, right? So more samples. Why shouldn't we just take as many samples as we want? Excuse me? Memory. So we have few reasons. So first of all is a storage capacity. But now we can overcome this kind of problems using, for example, virtual servers and so on. But this is a very good point. What else? Yes. Good. So sometimes, and okay, you know, it's not only sometimes. So we have more noise when Fs is bigger. For example, if I take a higher sampling rate, this might affect the level of the threshold here. Sometimes there is a relation in the method of imaging or recording that it affects the threshold. And then, for example, if I have a higher sampling rate, but the threshold is over here, look how many non-real spikes I take into my data. So this thing that I always want to see the relation between noise and the signal is called SNR, and we will talk about it a bit more during this recitation. Great. Okay, so is it now more clear what sampling means? Yes. 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 Great. So sampling is the fact that I was saving the recording at a specific time point, and quantization problem is exactly as you said. But sometimes they are about the same, because I'm saying, if for here, for example, the problem is that I can see that there are two peaks in the spikes, but the quantization of data allows me to save only one. But think that sometimes it is also the same when you're doing sampling grade, when you're doing just sampling problems. Great, yes. How, excuse me? Recording, okay, so here it's problematic to see it with this kind of data. Okay, so I'll show you something from my data. 1 minute. Maybe I'm thinking where to show you this, because this was a paper that I presented and I don't see it here. I'll just open a WhatsApp and I'll show you from the WhatsApp. So I'm sorry for opening a WhatsApp. It's only to show you something. So for example, in my project, I study eye movements and their relation to neural processing in V1. So what I want to show you is a paper that I'm working on. And we were wondering, we were wondering about the algorithm for detecting the eye movements that we were using. So for example, 1 minute, it's not here. So, okay, it will take me a bit of time to show you this. So I'll do it. Is it okay that I'll do it just after the break? So I'll have a few minutes to find. Okay. Great. So now I want to go on into firing grades and talk a bit about convolution, and then we will have a short break. Okay? Yes, Eric. What do you mean increase in bands? Mm-hmm. I still don't fully understand the question. Sorry.
You say that you increase the treatment, for example, to more actually capture the
Yes.
binarized two into one larger thing.
Yes.
But the same as saying large.
Yes. So for my sampling, the fact that I sample only for 1 minute, I'm interested only if there was a spike or not. So a frequency of 1 hertz is not good enough. It's not a good temporal resolution to distinguish between two events within the same duration, within the same bin. Okay, is it more clear now? Great. So now I want to talk about firing grades, because as I said, commonly what you will have is that you will have these spike frames, that you have these vectors of 1 and 0, and then you want to turn them into firing grades. So let's first understand, what does firing rate means? What do you think firing rate means? Yes. Great, but that really depends on how do you divide between them. So first of all, it can say that you have a time duration, delta t, right? And then you have this bin. For example, previously, we could say that the firing rate over here was 1 at this one, 0, 1, and 2, right? This was the number of spikes within each second. So here, this is the firing rate. This is the rate of spikes within each duration. And the duration could be, for example, 1 second. Now, another thing that we can do is the mean firing rate averaged across different trials or across a population. For example, I can take this 5 seconds over here and say I had 4 spikes within these 5 seconds, and then therefore, the average of the firing rate is 4/5, right? And another possibility, 1 minute, is to look at a very short time period. Sometimes we say, okay, we want to see it as an infinitesimal idea of the firing rate itself. I don't look at it as a step function that there is 1, 0, 0, 1, and 2, right? Do you understand what did I plot here? I plotted the function of the firing rate. So I can say that I look at it as something which changes within time. So for example, it can also look like this. And when I use this kind of interpolation, I assume that the firing rate is over delta t equals to 0, and I can interpolate in between. Okay? So now, please. Firing rate, I meant to write FR. I'm still thinking all the time about my response to our men. So sometimes I'm thinking where to find an example for problems with sampling. So this is why you see that I'm not fully here. Yes. The average. Ah, sorry. Yes. Yeah. It was not a C. It was, yeah. Here is another example for me not being here. Okay, so how do we compute the firing rate? So I plotted this kind of step function, but we have also this kind of smooth function. And now I want to talk with you about when we have this kind of input. Now, the first thing that you will need to do in your project is take this spike train and make from it a function that will either look like this or will be smooth like this. And I want to talk with you about the steps of doing such a thing and to understand what the steps mean. Okay, so let's see, for example, we have this spike train over here, okay? And what we want to do is to plot this spike train using bins, okay? How would that look like? So we have maybe what I'll do, 1 minute. Okay. And I will take this up. And Zoom people, there is some chance that you won't see it very good. And I'm sorry, I'll try to explain what am I doing. Great. What is going here? I don't know if you see it good. Is it okay what you see here? You'll make it. Okay, I just want to plot on the board instead of writing it from a new. Okay, so we have this spike trend, and what we want now to do is to make a function of firing rate, and we want to use bins size of 100. Okay, so in this bin, how many spikes do you see? 2. In this bin, how many do you see? I think I'll just do like this. This is okay. Maybe. You are right. Okay, so we have these 2 spikes here, and here between 100 and 200, how many do we have? 3, right? And here, how many spikes? 1, 2, 3, 4, 5. Great. And here? 3. And here we have, I think it's 1, and we don't care about this. Now, what is the firing rate? How do we calculate the firing rate? 1 minute, sorry. Nothing. So what does the firing rate is? So we know how many spikes there are within one bin, but this does not mean this is the firing rate. So the firing rate, if we have two spikes, it's the number of spikes over time when the time is given by seconds. So if I have 2 spikes within 0.1 second, how many spikes do I have? What is the firing rate? 20 hertz. So try to think about it from another direction. So if we have 2 spikes at 100 milliseconds, we have within each 100 milliseconds, we had 10 like this. So we have 20 at 1 second, right? So this is 20 hertz. So here, if I want the firing rate, I will just add 0. And then when I want to plot it, I will do it like this. So I have 0, 100, 200, 300, 400, and 500. And over here at 100, I had 20. And here at between 100 and 200, I had 30. Oh. Okay. And then it became bigger to 50. And then it decreased back to 30 and to 10. Okay, so this is how the function of firing rate will look like. And what I want you to do is that next time, if you want to understand it better, please try to solve the second section by yourself of 50 milliseconds and then by alternating 150. And please know that if you're alternating the bins here, you need to alternate the bins over here, right? So you will have 100, 100 to 150, and then 150 to 250, and so on. So also the x-axis will be interleaved. Okay? Right. So what is the problem with such an idea of firing rate just by using bins? Yes, Julia. So, for example, when you had this function, so you have 100 and then here 150. 250, 300, right? So for example, it will look like this. You see it? So you have long and short, long and short. Yes, they are interleaved within each other. Yes, yes. So this is what, this is again just to understand the idea of bins. Okay, and the reason that I want you to do it is the following one. So that, not this screen. I want them to see this screen. Great. So what is the problem? 1 minute, sorry. I don't see it. Okay. So what is the problem by using bins? When I use bins, I have a problem, a scientific problem. Yes. Okay, so it is really highly dependent on the temporal resolution, because if I take 100, it will be, all of it will be 20, and if I take 50, here it will be 1, and here 1, but here it's not this. Here, for example, it will be 1 and 3, and then it really depends on my sampling, right? On the binnings. But there is another problem, because I have this spike train, and I give one student the spike train from its beginning, and he will have these values, but then another student will have it a bit later. For example, the recording device began 50 milliseconds later, and then it will have very different values, right? Like you see over here. So we have two problems. First of all, this function is non-smooth, so it's always about averaging the number of spikes. And furthermore, another problem is that it depends on where your bin begins and ends. Okay, maybe I'll explain it again in Hebrew, because I see that some of the Hebrew speakers, it was not fully clear. הבינים שאני בוחרת, אני יכולה להחליט איפה מתחילים, ואיפה שהם יתחילו זה ישפיע על התוצאה, אוקיי? ואז יהיו לי שתי פונקציות שונות שמייצגות את ה-firing rate, אוקיי? את קצב הירי. So I have two functions, so which one of them is the right one? Which one of them is the right one that I want to describe my neuron with? Its firing rate. So why not? First of all, you jumped into why using smoothing, okay? So first, please explain why smoothing helps you with this problem. Okay, so tell me for the first reason. The problem is that we have two functions. Each one of them describes the same spike train. So which one is the right one to use? This is the main problem that they want to deal with. Yes.
I don't know where you want to start recording.
And when did you start? Right. So how do I choose? Should we choose one? I want to measure the firing rate. I want to know if the neuron increased its firing rate due to an input or not.
All of them are in the way one.
Great. Why?
All of them start at the same point. So baseline. That's what's best.
Do you want to try? I think that you're in the right direction. Would you wish to
Keep recording at the same time, these will be correct for each measurement for you.
But this is, but you say that the problem is when did they start the recording?
Yeah, that's the problem.
Right. But there is another problem because, as you said, for example, I could start it here and just not record this spike, right?
Okay.
But then you have different function. Which one is the right one?
Right one. As long as you keep, as long as you just start recording in the same place for all of the measurements, doesn't matter. It's start.
Okay, I want to do it a bit more accurate. Do you have an idea, Shil? Great. So the problem is that these windows are non-overlapping windows, right? Because the fact that I have to do this jump each time creates the problem that it depends where I start the bins, right? Maybe this was what you tried to explain. But I say that if, for example, I had a problem in the recording device and it started just a bit later, then I have a different function. But these are just about the same spike trends, okay? So what we need to do is to use overlapping windows. So this is about the very basic idea of convolution, okay? So what does convolution mean? Convolution is this window moving each time by a small step, and the windows are overlapping within each other. And then I save for each window, I save its, how do you call it? Its output at the middle point of the window itself, okay? So basically, convolution is a moving average. And this is a very important thing. Now, please notice that even if we use the overlapping windows, what can happen, another problem, is what size of window do we use? Because, for example, if I take a wide window, then I will have a much smaller values, right? Much more smooth function. Okay, and if I have a smaller window, then I will keep all of the peaks. So how do you decide what kind of a convolution to take? For example, you had these samples like this. This is not good. Right. How do you choose your convolution window? Yes. Exactly. So convolution, beside the fact that it helps us to keep the same function the same, for example, here we had this problem that this function looked like this, and then when we used another one, it looks like this, right? Do you remember the previous one? So convolution will help me that all of this will look like this. But a wide convolution window will take, for example, this area, and we'll just smash it away. We won't see it anymore because a wide window will have a wider number of samples within each one, and then it distorts the quantization more, okay? So the basic thumb rule is that we want to use convolution as small as possible, but with the best SNR. Okay. So this is funny because when I did this course, they told me it just depends on what your supervisors say, but it's not true. In science, we don't want to use big convolution windows because it will distort our data, but we don't want to have too much noise. Okay. So we need to measure the differences. And this is just about measuring SNR, okay? The signal to noise ratio. So the last thing that I wanted to say was, okay. So you know that within 2 minutes you'll have the break, okay? So just stay tuned, we're about to go to a nice break. So I just wanted to say here is a nice computational hand-by-hand convolution, okay? So you can try it. And I just wanted to say that when we do convolution, we can use different types of windows. For example, this rectangular window, it's an average with the same size of bins. But then you can say, wait a minute, I don't want to average all the bins in the same way. Some of them are more important, those that are in the center of my bin, and some of them are not, okay? And then you can reduce the level that the outputs are affecting the convolution. And another one can say, wait a minute, if I had this spike train, I don't care about the spikes that were before this 0 point. I care only about the spikes that are after. So this is a causal window that I take only the spikes from now on to my average, not the spikes that were before, and I assign them to the beginning of the window. Okay? Great. So, you know what? Before we see the example of what convolution does and the SNR and all of these things, take 5 minutes break and we'll be back at the hour of 3. And I'm looking for an example with eye movements for you. Yes. I just want you to see how the size of the bin affects the temporal resolution. But still, it still keeps the problem of the fact that the bins are non-overlapping, and then you have this problem. 1 minute, I'm just looking for it's okay, Armin. I'm looking for an example. I don't know if all of you want to see it, but please come. I want to show you. So I don't know if to show it in class or not, but for example, I am using this eye movement data. Where is it? Here. And this is, yes, all of our monkeys are, with this, here, okay. So I have this kind of data, it is eye movement, and then you can see the noise, right? All these fluctuations around. And then when I use my algorithm to detect, you see that it misses over here at the beginning. And the reason it misses is because it's around the fluctuations, right?
What is it missing?
It's the beginning of the red line should be the microsaccade, the big change in the eye movement, right? And the reason it misses across this line is that the beginning should be before we see it by our human eye, but all these fluctuations disturb it, right? So this is why I reduced the sampling rate, and then you can see that the number of fluctuations it is much smaller. I reduced the sampling rate and yes, and used a kind of smoothing function, not convolution, a different one, which is more commonly used in the eye movement field. And then you can see that now the detection is accurate. So this is an example of what I was saying about lowering the sampling rate. Sometimes it increases the SNR.
I didn't see the difference in the detection.
So here, maybe this one. So you see here, you have also this part, the black one.
Yeah.
And then when you look here, you see that here, the detection is more accurate, right? And the reason it was not accurate is due to the problem in the noise
It's
here.
easy to see the change.
Exactly.
Yeah.
So this is a very nice example of what
Yeah.
we're talking about.
Mhm.
Do you think I should show it in class or?
I think it is important to
Okay.
understand.
Okay, so I'll just send it now and I'll download it to my WhatsApp from the computer.
And I still have the same question from
Yeah,
WhatsApp.
so
I
please
was thinking that we would do like equal to
equal 50. So try and see if it, again, the problem is not the size of the bin because you can do as small as you want.
like
But-
what would give this like 50, then 100, then 50.
I just wanted to show you that even if you use different types of, for example, one student told me, okay, so just use different size of pins for each number of spikes. If you have a little number of spikes, so use a small one and then a big one. And I just want to show you that even if you change, this does not solve the problem, that it is highly dependent on where you began your measuring, right? Because then you will have different functions to describe the same spike frame. You're welcome. Okay, should we go on? What do you say? Okay. So I had a very nice discussion during the break with Armin and Araceli. And I want to show you something. Armin asked a very good question. 1 minute, I want to put it on the second screen. She asked me, okay, I don't fully understand how subsampling can help you in reducing the noise, okay? Or how the noise is affected by the sampling rate itself. So here is an example from my study. I study eye movements, and when I use eye movements, I want to detect microsaccades. What are microsaccades? These are very fast eye movements that are not very big. They still give you about the same image on the retina itself, but they are very fast. So, for example, look at the detection here, right, of the microsaccade. This is the algorithm that I use, and it doesn't matter how this algorithm is working. But you can see that the fact that there are so many fluctuations and so much noise around here, it makes this algorithm to dismiss parts of the microsaccades. Okay, so what did I do? I took the eye movement and I subsample it. instead of one sample within each millisecond, I subsample it to 500 hertz, which is, what is the duration of each sampling? Duration between sampling, 500 hertz is 2 milliseconds between two samples. So, and beside that, I also use a smoothing algorithm, not convolution, another type which is more commonly used for eye movement. And then you can see that now the algorithm had no problem in detecting the full eye movement, right? So we are all, so I want us to understand better the idea of noise by having this kind of visualizations, right? So here is an example why high sampling rate, in one way, it can help us to detect better changes and to have more accurate recording of brain signals, yet the noise is much bigger. And then I cannot do things with my data if I want to understand it. Okay, for example, by detecting the specific full eye movement. So this was a nice example. And another thing that I want to show you is again, when we use convolution. So you can see what happens to an image. This is again from our studies in the lab. So we have this very pixeled image over here. And in this image, this is an image of the brain using VSD, if you heard the Chavutal lectures. And where you see this white blob, this represents that the neurons here were highly activated. Now, when I see this image over here, and I want to make it less noisy, because many of the pixels around here mean nothing. They are just noisy. So I can use bins of 4 by 4, and then I see this kind of image. But then I can use a convolution. And you must say that first, this is the most prettiest one of all of them. And second, this is much more clear. I feel that I can really understand where the stimulus, where is the blob. And here it is not fully clear, and here also. So in a way, convolution, one of the things that it does, it helps us reducing the noise, and by so understanding better the transition between areas in the space or in the timelines. So here is another example, and this is just about the first project that you're going to do. You have a question about firing rates, and then you are given with spike trends like this one, and you're asked to use bin count, right? Did you see this in the first project? This is, I think, question 2 or something like that. And then you can see that you need to, when you bin them, you have this kind of function. But then when you use a convolution of a sliding window, you have something better. And when you use a convolution of a Gaussian kernel, you will have something that is even less noisy. Okay? And this is also, for example, a sliding causal kernel. This is also a very good one. So why not using convolutions all the time? So I must say that I took it from the internet, and they didn't say about the size of the causal kernel. So for example, if this one is just wider, so it will look about very similar to the sliding Gaussian. So it really depends on the size of the kernel and not on the method itself. Okay, so why not using convolutions all the time? It helps us, it clears the noise. Why not using convolution whenever you... Okay, so every time I want to throw out noise, I always might pay by throwing some information, right? What else? Maybe the Hebrew speakers remember, I'll ask again the question in Hebrew. מה הבעיה בשימוש בקונבולוציה? למה לא להשתמש בקונבולוציה כל הזמן? Maybe you remember it from previous studies in your first degree. It's okay if not. So one of the main problems in convolution is the distortion of the time, right? Because every time that you use a convolution, you make your sample bigger. Okay, and there is the computation here in the recitation notes of how bigger it is, how much bigger it is here. So if you had a vector of n and you used a convolution of n size, then the new vector of the convolution will be n plus m minus 1. So you have distortions of the time axis. While before you were very accurate, there was a delta function which gave you about the precise value at a given point. Now you have a problem because when you use the convolution, you are not precise. You were averaging other values around this point. Okay, so another reason why not using big windows is the reason that the bigger the window is, the distortion is bigger. The distortion of the time axis. Yes. No, once you use convolution, you have to pay by the temporal resolution. But then again, you had a problem in the beginning that you don't know what is noise and what is data. So you're reducing the noise and then you left away some data. So you don't know in advance what will be the outcomes. But this is always around, I think this is one of my favorite things about neuroscience, that you have to find the right balance between cleaning the data and between leaving some noise. And some of you who take, for example, Hamutal course about, oh, she left out the spontaneous activity. Okay, there was a nice subject in the neurophysiology course that she was talking about what is noise. And there is something in neuroscience called spontaneous activity, which is always considered as noise, as baseline. But then she shows some studies that show that this is not noise. Some of the most important things that happen in the brain, for example, consolidation and learning and so on, and memory happens within this time. So, okay, so we were talking about noise, and this is just about the right time. Yes. N is the size of the signal. M is the size of the convolution. And -1 is just a constant that you always take off. Okay, and this is the outcome. And some times you can use, for example, in MATLAB, when you do equal or something like that, it will just crop the convolution to be the same side, but the distortion is still there. Yes. Yes. So you know what? I didn't show you everything because we don't have enough time. Okay, maybe here. I want to show this. Okay. So practically, we were talking about a moving bin. And if you have this signal and you just move your convolution across it, so you can see what happens, right? So instead of just a very rough distinction in the step function, now you have this linear function which goes up here and down here. And you can see that the base of this triangle is wider. So what size is this base? It's the size of this square plus the size of this square -1, okay? So within each sample or each number of samples, the convolution distorts the time. So even if I use the Python or the MATLAB that I can say, don't make the vector longer, make it the same size, okay, as the one before. So note that the distortion here in the triangle, I can crop here, but I still keep the distortion of the time itself. Okay, was that more clear? Okay, so now what I want us to talk about, that we were talking about convolution as a kind of a filter for reducing noise. And I was talking a lot about noise today, but we don't know how to measure noise. And this is one of the questions in your project. What is the noise? And I want to explain what noise is. So we are talking about two types of noise. The first one is called an additive. I use here the Xi to show the noise itself. So for example, if I have the firing rate, and this is a function of the array of the spike train plus a noise, this is called an additive noise. And another possibility is called multiplicative noise. For example, that I can add to my real function, I can add noise, which is over a Gaussian or just any function which can be, okay? But the main idea that I want you to remember that when we have a scientific study, we have this, the rate, or for example, the recording, and we are looking for the function. And the question is, how can we get from this into this? Sometimes what we can do is just find the noise itself and just reducing it. But sometimes we can do other things, for example, statistics, that we can bin together more and more trials. And then this one becomes more closer to this one. Okay? And this is the central limit theory, will just one of its versions that the bigger that you have samples or the bigger that you have trials, then the relation between the recording and the real phenomena becomes bigger because the noise is reducing towards zero. Okay? So some of the noises, of course. So I was saying all the time noise and signal and noise and signal, and now I want you to know, how do we measure the relation between noise and signal? Yes. The more trials you have, yes. Or we use samples as the dots, but we will be more accurate. If you let the monkey or the cell or the person to do again and again the same action, the more trials you'll have, you will be more accurate in the relation between your recordings and the real brain function. But what is the problem? Okay, well, you know what? I'm just running through the recitation today because this is really a nice recitation. I don't know if you enjoy it like me, but I really love it to talk about science. Okay, so after this one, I want to talk about stochastic processes that maybe you understood now when I say repeating again and again, you have another problem, because when you repeat again and again on the same action, then the action that you did at the 100 time is not the same one as you did as the first time, right? And this is due to how the brain works. And this is called the assumption of ergodicity, that your paper that you need to read, and you are allowed to read in pairs and to use ChatGPT to understand it, is just about the fact that we cannot use the assumption of ergodicity in neuroscience. Okay, so back to the SNR and back to the fact that we want to evaluate the relation between signal and noise. So we have these two formulas over here for SNR. Who would like to explain what SNR means just by looking at it? Yes. Right. And what does that mean? Great. And it is squared, right? Over here, after the square root, what do we do? We take a root, okay? If we want to go back, but we can also leave it like here. This is called mean square, and this is root mean square, right? So after I divided between them, why is that not enough to talk about SNR? Why do we need all of these logs and so on? What the log does, maybe some of you remember from the mathematical reinforcement. What does logarithmic scale does? So I'm not interested on the question, is the noise, for example, let's say I have two recordings. In one of them, the noise is twice as the noise in the first one, right? So I want to compare between them. But if the noise is only twice and the noise was very small, it means nothing. I'm interested in the relation between the signal and the noise, and I want to give a logarithmic scale because I want to know the difference between 1 and 2, which is 10 times difference, right? So for example, 2 decibel of SNR is, what is the relation between the signal to noise in 2 decibels? If we have SNR equals 2, what is the relation between signals and noise? Let's do it together. So 10 log 10 of signal to noise, both of them are squared. This equals 2, right? So the log signal to noise ratio is 20, right? Maybe I'll do it just, sorry, 0.2, right? So the signal to noise square is 10 times 0.2. And then we can have a root square of O power by 0.2. Okay? And this is, for example, this is around 1. Okay? So again, it is commonly used that we talk about SNR in logarithmic scale of decibels. So when you are asked, for example, in the project, what does SNR of 2 or 3 or 5 or -1 means, you need to do all of this analytically. Okay? And the relation will be by tens. Okay. So the last thing that I want to talk with you about, these are all of the mathematical convolution, and I took it out of the project, but commonly we ask if you use a convolution, how it affects the SNR, and then you need to calculate the SNR and compute it and so on. But I want us to talk, and here I gave a nice thing, just read all of this. I gave her a nice idea that it says that practically the brain, the neurons are performing a convolution within their input. So it's really nice. Okay. So tell me, I know this is about the 10 last minutes of the class. Do you want to hear a new subject, or do you prefer to talk about stochastic processes next time? What do you prefer? You look really tired, so this is why I'm asking. Next time? Okay, are you okay with next time? Okay, so I'm okay with next time, and then we can relate it to Poisson renewal processes. Yes? Yeah, I already published the first project. So I think that at least you can do the firing grade. Let me look at it. Let's talk about possible things that you can do from the project. And the reason I'm telling you now to do it is that each project takes about 30 hours of working. Okay, if you understood good the things that we are talking about during the recitation. So I highly recommend to start doing the project today. And in the project, you can do, maybe I'll ask Sophie also to write it in the WhatsApp group. Okay, so in the project, you can already start. And not this one. Here, signal sampling and SNR you can do, firing rates and convolution. And we are left only with 2 questions. So please start sections 2 and 3. Don't leave it to the 20th of May. Okay. And there is a recitation quiz that after each recitation you are required to answer. So please fill in the quiz. If there is a question about stationary and stochastic and ergodic, do not answer it. I'll just, Sophie, let me know if there is something which is redundant, and I'll take it away or replace with another question. Okay? Maybe, you know what, Sophie, can you check within the next hour? Yeah. It's in the website itself. You have the recitation tab, and then it's until the next, each time it's until the next class of Izal. So you have by Monday. So for example, so this one still is until Monday, but it's really easy 5 questions that I want you to answer today, tomorrow, or at Sunday max. Okay? It's really easy, and if you find yourself struggling, please write me, and I allow you all of the quiz recitation quizzes you can do together in pairs. Okay? Because they are used for me and not for you. This is my way to fully understand what did you learn during the class. So if you didn't understand anything, don't worry. You need to have at least 60. It's about 2 mistakes. It's not that many. But then I can understand if I need to re-explain anything. So I think you can do it, as far as I remember. So yes, you can do. Sorry. You have there a question about the EEG, right? Sophie, I think the last question is about the EEG, as far as I see. 1, 2, 3, 4. Oh, no, I took it off. Okay. So I think you can do it. No, no classes. On Sunday, if you wish, you can come to the mathematical reinforcement. in which I will talk about, let me check. Maybe about, no, I think that I'm not sure if we will have something on Sunday, because I'm not sure if I want to talk about stochasticity and Poisson distribution only for a very narrow subpopulation of the class. So I think that on Sunday we won't have a reinforcement either. So we will meet only at Wednesday. I think that no need for mathematical reinforcement because I don't want to have a gap. I open this evening. You will have my reception hour, and as always, if people have questions during the week, they can write you, and you can talk with me. You or Noah, I hope that it is not too much for you, but I just can't handle it with all of the course students. Okay. I think not, but I will let you know for sure by sending a message to Sophie. I will look again if I think there is something with which is mathematical, but I don't want to talk with you about stochasticity and not with everyone. Okay? You're welcome. Yes. Yes.
You have multiple replicates of